Hello everyone. In this presentation, we are going to discuss an important topic in concrete technology, quality control of concrete. Quality control is essential because concrete is not simply a material that is mixed and placed. Its final performance depends on controlling the complete process starting from the selection of materials and continuing through mix design, batching, mixing, transportation, placing, compaction, curing, and testing. The main objective of quality control is to ensure that concrete achieves the specified strength, durability, and workability while maintaining uniform quality with a minimum variability. The difference between quality control and quality assurance. Quality control or QC consists of inspection, testing, and corrective action during construction. In simple words, we can say QC checks whether the concrete being produced and placed is meeting the required standards. Quality assurance or QA is different. It consists of planned systems and procedures that give confidence that the specified requirements will be achieved. Therefore, QC is mainly product and process focused, while QA is system focused. Both are necessary for reliable concrete construction. Now, let us move on to the major factors affecting concrete quality. The first factor is materials. These include cement, aggregates, water, and chemical admixtures. The second is mix proportioning. Important parameters include the water cement ratio, cement content, aggregate grading, and admixture dosage. The third factor is production. Batching accuracy, mixing efficiency, and the condition of equipment have a direct effect on uniformity of the concrete. The fourth factor is site practice. Transportation, placing, compaction, and curing must all be properly controlled. Finally, environmental conditions such as temperature, humidity, rain, wind, and exposure conditions can influence concrete performance. Now, let us consider cement quality control. So, we must verify the cement type, grade, and manufacturer against the project specification. The manufacturing date, storage condition, and test certificate should also be checked. Cement should not contain lumps or show signs of moisture contamination. It should be stored in a dry, raised, and covered area. The first in, first out principle should be followed so that older cement is used first. Where required, cement can be checked for properties such as fit, fineness, setting time, soundness, and strength. So, next is about aggregates. Aggregates occupy a major portion of concrete volume, so their quality has a major influence on concrete performance. We should check their source, cleanliness, particle shape, and grading. Silt, clay, organic impurities, and other deleterious materials must be controlled. Aggregate moisture content is particularly important because surface moisture changes the actual amount of water entering the concrete mix. The grading of fine aggregate and size distribution of coarse aggregate should remain reasonably consistent. Depending on the project requirements, tests can include sieve analysis, specific gravity, water absorption, impact test or crushing test, and soundness. So, next is about water and admixtures. Water used for concrete production and curing must be suitable. Normally, potable water is generally acceptable. Admixtures must be selected carefully and their type, dosage, and compatibility with the cement and other materials should be checked. One very important rule is do not add uncontrolled water simply to improve the workability. Adding extra water can increase the water cement ratio and reduce the strength and durability of the concrete. Admixture dispensing system should be calibrated and the dosage should be monitored for every batch of the concrete mix. So next is about mixed design and water cement ratio. Mixed design aims to achieve the required characteristics, strength, workability and durability. Water cement ratio is one of the most important parameters because it strongly influences the strength and permeability. So we should use minimum water content necessary to obtain the required workability. We also need to account for aggregate moisture and absorption. Before production, trial mixes can be used to confirm strength, slump and other performance requirements. So now is about batching and weighing. Accurate batching is essential for producing uniform concrete. Cement, aggregates, water and admixtures should be measured using calibrated equipment. Weigh batching is preferred for controlled concrete production. Aggregate batch weights must be corrected for surface moisture. The quantities used and production time should be recorded. Equipment such as gates, load cells, water meters, and admixture dispensers should be inspected regularly. After batching comes mixing. The mixer capacity and mixing time should be suitable for the concrete and the equipment. Material should be loaded in a proper sequence, consistent sequence. The purpose of mixing is to obtain uniform distribution of cement paste, aggregates, and admixtures. Undermixing can result in non-uniform concrete, while inappropriate mixing or excessive handling can create other problems. Mixer blades and drum condition should also be checked periodically. So, next is the most familiar fresh concrete test, slump test, to be followed at the site. The slump test gives a rapid indication of the consistency or workability of the fresh concrete. For a proper test, a clean and damp slump cone is placed on a firm and level surface. The cone is filled and compacted according to the applicable standard procedure. After the cone is lifted, slump is measured immediately. An unexpected change in the slump may indicate a problem with batching, aggregate moisture, or admixture dosage. So, besides slump, we should monitor concrete temperature, particularly during hot or cold weather. The concrete should be checked for uniform appearance and for the signs of segregation or bleeding. The time of batching and arrival at the site should also be recorded. Where specified, air content should also be checked. Importantly, fresh concrete test results should be traceable to the corresponding batch. Next is transportation and placing. The time between mixing and placing should be minimized. During transportation, we must prevent contamination, segregation, and excessive loss of workability. Concrete should be placed as close as practical to its final position. Uncontrolled addition of water should be avoided. Placing sequence should be planned so that undesirable cold joints are avoided. Once concrete is placed, proper compaction is extremely important. Compaction removes entrapped air and improves density and bond. Internal or external vibrators may be used depending on the application. Under vibration causes honeycombing and poor compaction. On the other hand, excessive vibration can promote segregation. Special attention is required around reinforcement, corners, and embedded items. Operators should be well trained and vibration equipment should be properly maintained. So next comes curing. Curing maintains the moisture and temperature conditions required for hydration. Common methods include ponding, wet coverings, curing compounds, and membrane systems. Curing should begin as soon as practical after finishing while avoiding damage to the surface. Concrete should be protected from premature drying, excessive heat, cold, and vibration. Insufficient curing can reduce strength and durability and increase cracking. So next is about hardened concrete testing. Concrete specimens such as cubes or cylinders are prepared, compacted, identified and stored under controlled conditions. Compressive strength is commonly assessed at specified ages, normally after 7 and 28 days. Testing machines must be calibrated and correct loading procedures must be followed. For each specimen, important information such as identification, casting date, age, dimensions, and failure load should be recorded. Test results must be interpreted according to the acceptance criteria of the applicable standard or project specification. So sometimes we need to assess existing concrete without causing major damage. This is where non-destructive testing or NDT becomes useful. The rebound hammer provides an indication related to surface hardness. Ultrasonic pulse velocity, that is UPV, can help evaluate concrete uniformity and identify possible discontinuities. Core testing can provide more direct information about concrete strength when required. However, NDT results should be interpreted by competent personnel and, where appropriate, correlated with other information. So let us look into the common concrete defects. Honeycombing can result from inadequate compaction, congested reinforcement, or unsuitable workability. Segregation can occur because of improper handling, excessive vibration, or an unsuitable mix. Bleeding is associated with excess water or poor mix characteristics. Plastic shrinkage cracking can occur when the surface loses moisture rapidly. Cold joints can develop when there is an excessive interruption in concrete placing. An important principle is that we should identify the root cause of a defect before deciding on repair. Let us summarize a practical site quality control checklist. First, verify that approved materials and current test certificates are available. Second, check equipment calibration and batching accuracy. Third, confirm that the concrete mix designation and approved proportions are being used. Fourth, perform slump and temperature checks as required. Fifth, inspect reinforcement, formwork, and embedded items before concrete placement. Next, sixth is ensure proper compaction, finishing, curing, and sampling. Finally, maintain complete inspection and test records. The next important topic is statistical quality control. Concrete strength naturally shows some variation even when production is carefully controlled. We should not look at only one test result. Test results can be used to monitor average strength and variability. Control charts can help identify trends before they become serious problems. Standard deviation and coefficient of variation are useful indicators of consistency. Acceptance should always follow the governing code or project specification. The purpose of the statistical quality control is not simply to reject concrete after failure. More importantly, it helps us identify process problems early and correct them. So let us conclude. The most important lesson is that quality concrete is the result of controlling the entire process, not merely checking cube strength. We need to control the sequence, materials, mix design, batching, mixing, transportation, placing, compaction, and curing, followed by systematic testing. We should use calibrated equipment, trained personnel, standardized procedures, and proper documentation. So, whenever an abnormal test result occurs, we should investigate the cause promptly rather than simply accepting or rejecting the result without understanding the process. Good quality control improves strength, durability, service life, safety, and economy. As civil engineers, our responsibility is not only to produce concrete that passes the test, our responsibility is to produce concrete that performs reliably throughout its intended service life. Thank you.